Thank you very much. I would like first to thank the organizers for inviting me. So my tutorial will be sadly quite technical, but not in the sense that it's complicated. It's more in the sense that it's technique-oriented, not as motivated as was Demir's talk. I tried to make it as self-contained as possible, which means also that sadly there will be some trivial parts will be boring for the experts. And of course, it's totally impossible to make it totally self-contained. So for the beginners in computability theory, they will not be able to understand this. So I try to make a good trade-off between making it sufficiently boring for the experts and not understandable for the beginners. I'm going to talk a lot about forcing, but let's just first motivate it. So Demir made a very nice introduction to reverse mathematics. I'm still going to make a quite short one, mostly because I already wrote the slides, so I want to rentabilize them. There are many ways to motivate reverse mathematics. One that I like particularly is mostly due to Steve Simpson as a partial realization of Hilbert's program. So you all know this crisis of foundations of mathematics and the apparition of paradoxes, and people started to consider that the fault was the use of infinity in mathematics and to question it. And Hilbert tried to save infinitary techniques in mathematics by by trying to identify an infinitary system which would capture infinitary mathematics, and then within this capture finitary mathematics and show some reduction, showing that every proof that could be done by infinitary means could be translated into a proof, a finitary proof. Of course, this was proven not to be possible by Gödel, by the Gödel's incompleteness theorem, because the consistency of arithmetic is a finitary statement which is not provable by finitary means. But reverse mathematics is trying to save this finitistic reductionism program from Hilbert by showing that even if there are some statements which are provable by infinitary means which are not provable by finitary means, most of the time in ordinary mathematics, in everyday life mathematics, this actually works. So most of the theorems that you actually use, or not necessarily you, but other mathematicians, are already provable by finitary means, or at least their finitistic consequences are provable by finitary means. So it's a way of partially realizing Hilbert's program. So the idea, and you all know this, is to take a theorem and to analyze it, try to find the weakest axioms to prove it. And how do you know that these are the optimal axioms to prove the theorem? You just reverse the arrow, which is the name of reverse mathematics. So we have to fix a frame, and we use second-order arithmetics. And it could be quite questionable to use the second-order arithmetics to capture all mathematics, while we have a more obvious choice, which would be set theory, the language of set theory. But actually, it has. So the work of Hilbert and Bernays showed that second-order arithmetics is sufficiently strong to express a lot, modulo coding, naturally a lot of statements. And we have the advantage that every object in second-order arithmetics are integers, are coded by integers or sets of integers. And we have a very good notion of computability for integers, so we can take all the framework of computability theory to put in the reverse mathematical program. So we want also to work on a base theory, because if we just want to work over logical equivalence, even slight modifications of theorems or equivalent versions of theorems would be unequivalent, and especially because we are working modulo coding, because we want to make it fit to the second-order arithmetics. We really want to be able to prove the equivalence to show that there is some kind of robustness in the formulation of the theorems. So we want to state a base theory, and for this we start with Robinson arithmetics, which is a different choice from as base theory as Demir did. Demir chose the discretely ordered commutative summing. It's almost the same. If you add just a little bit of induction, both theories are equivalent. So it doesn't matter we can choose Robinson arithmetics or discretely ordered commutative summering. And actually, I like Robinson arithmetics because everybody knows piano arithmetics, and we can just say Robinson arithmetics is piano arithmetics without induction. So it's a good way of saying it. But it's somehow cleaner mathematically to say to consider discretely ordered commutative summering. So I thought choice. Then we want to have some comprehension scheme, and of course, because of the correspondence between definability and computability, we have to be a bit restrictive in the choice of formulas for which you have the comprehension scheme. So because we can classify second-order formulas based on alternations of quantifiers. And so here you are sigma 0 n if you have n alternations of first-order quantifiers, followed by just quantifier-free or bonded formula. And you are pi 0 n if you start by a universal quantifier. So yeah, sorry. So that's the part where it becomes boring for the experts. So there is this correspondence, and we know that a set is computably enumerable if and only if it is a sigma 0 1, and you are computable if and only if you are both sigma 0 1 and your pi 0 1. And so it goes at every level of the arithmetic hierarchy. So a set is 0 to the n CE if it's sigma 0 n plus 1, and 0 to the n computable if it's delta 0 n plus 1. Because of this, we want the comprehension scheme restricted to computable sets. We want to close, to capture computable mathematics. But being delta 0 1 is not a syntactic property, it's semantic in the sense that it depends on either a base theory or a structure. So here we use a trick saying you are delta 0 1. So we use a trick of saying for every pair of formulas, one being sigma 0 1 and the other being pi 0 1, if there are equivalents, then we know that it's going to be a delta 0 1 predicate, so we can set the existence of a set. So it's a very small syntactical trick for that. And then we have the induction scheme. And at first sight, it's a bit strange to want to restrict the induction scheme because it seems to talk only about the integers, and integers being finitary objects. We want to the finitary objects are computable, so why wanting to restrict the induction scheme? And yeah, and the induction scheme actually is equivalent, so level-wise equivalent to the bounded comprehension scheme. So which states not the existence of a set of all the elements satisfying the formula, but of all the initial segments of a set of such a set. And somehow then, restricting the induction scheme, it restricts the complexity of the finitary objects of your model. That's how you can think of it. There are many ways to justify it as well. Sigma 0 1 is the right level where you can make, for example, you have a good notion of infinity for sets. So to say that you are unbounded or to be in ejective correspondence with the set of integers, you need sigma 0 1 induction, and it's often sufficient to make all our coding and so on. So RCA0, it's just Robinson arithmetics, so saying that the integers behave well, plus sigma 0 1 induction and delta 0 1 induction. So yeah, still, it can be a bit unsatisfactory to have sigma 0 1 induction because somehow it says that the CE finite sets belong to the model and not just the computable ones, but that's something to be discussed later maybe. So the early study of reverse mathematics showed that mathematics are very structured from modulo RCA0, so computationally. In the sense that you have RCA0, and modulo RCA0, if you take a theorem of everyday life, it will likely be either provable already in RCA0, which means that it's computably true, so it's already part of computable mathematics, or it will be equivalent to one of these 4 other systems, which are even linearly ordered by logical implication. So it's very, very well structured. Of course, this is only an empirical phenomenon, in the sense that it's not a theorem, and there are counterexamples, and you can build very artificial counterexamples. But there are also natural exceptions, and historically the most important exception is a Ramsey theorem for pairs, coming from Ramsey theory, which is not only not equivalent to any of these subsystems, but it's not even linearly ordered with these other systems, with Wikenix lemma. So a big part of modern reverse mathematics is trying to understand why, to understand this exception phenomenon, what is specific about combinatorics or Ramsey theory, what makes it different from the remaining parts of computability of mathematics, and is it just a human bias or whatever? And so Demir already showed you one picture. This is not exactly the same, but it's still showing the mess of reverse mathematics when you try when you explore other statements from Ramsey theory. So it's really a bias because it's still true that if you take an ordinary theorem, it will likely to be part of the big five. But because we are interested in exceptions, we will study especially failures of this, so it's why it looks like a mess. But it does not invalidate the structural phenomenon. So in reverse math, how do you prove a separation? So if you have two statements, P and Q, you want to show that P does not imply Q. So it is often the case that implications are not that complicated and separations are rather complicated in reverse math. And so a lot of focus is on separation rather than implications. So basically, we want to build a model of P, which is not a model of Q. And the model witnessing the separation, it's always nice to have it as close as the standard interpretation as possible. And so we like to work with omega structures, that is, models for which, structures for which the first order parts are the actual true integers with the natural interpretation of the order or the addition of the multiplication, which means that the only parameter of this structure is the second order part. And so an omega structure is fully specified by its second order part, so which means by the set of reals of it. And there exists a very nice characterization that Demir already mentioned of the omega structures, which are models of RCNots. These are models so that the second order parts are Turing ideals. So a Turing ideal is just a collection of sets which is closed downward under the Turing reduction and which is closed under the effective join, so the joint union. And there are not that many natural Turing ideals. In the sense that, for example, the collection of low sets is not closed under effective join. So usually it's the effective join which makes it fail. But being computable is a Turing ideal, and there exists a very nice characterization of the countable Turing ideals in terms of pairs, so A and B. So you are a countable Turing ideal if and only if you can be expressed of this form for pair of sets A and B. It's very nice. And so, as I said, Friedman proved that you are a model of, so an omega structure is a model of RCNout if and only if the second order part is a Turing ideal. So we shall, during this talk, only consider theorems which can be expressed as problems in terms of instances and solutions. So, for example, the intermediate value theorem says, so it can be seen as a problem for which an instance is a continuous function, which changes its value over an interval, and a solution is just a zero of this function. Or Koenig's lemma says that every infinite finitely branching tree admits an infinite path, so an instance is an infinite finitely branching tree, and the solution to such an instance is an infinite path. And so we want to understand how hard is it to find a solution given an instance. And furthermore, the problems that we consider are expressible in second-order arithmetics as pi12 formulas. So these problems are of the form for all x, so for every x, if it is an instance, then there exists a y, which means that it is a solution to x, where phi and psi are arithmetic formulas. So it's easy to check modulo proper coding that both previous problems can be expressed as pi12 problems. So given two pi12 problems, P and Q, how to prove that P does not imply Q over RCNots? And so we want to build a separation over omega models. So our goal is to build a Turing ideal which satisfies P, but does not satisfy Q. So by satisfying P, it means that every P instance in M has a solution in M as well. So to construct a model of RCNout plus P, so we are going to build such a Turing ideal. So we start with let's say, the trivial Turing ideal of all computable sets. And at step n, so we have a Turing ideal, which is of this form, set of all z which are computable by some set u. So it's what we call a topped Turing ideal, or topped model. And then you pick an instance of your problem P in Mn. You choose a solution y to x, and you have to carefully choose y. But we are going to discuss this afterwards. And then your next Turing ideal is the set of sets which are computed by y join u. So you have access both to u and to y. And if you are careful enough, so if you fix an appropriate order for choosing your instance, if you let M be the union of these models, so which are an increasing sequence of models of Turing ideals, then this will still be a Turing ideal, but it will be also a model of P. And because it is a Turing ideal, it is a model of RC0. And if we choose carefully our sequence of instances, then it will also be a model of P. But the difficulty is we want to separate P from Q, so we don't want this to be a model of Q. And when you add, so when in the step 2, when you add a solution to your model, you might also add solutions to instances of Q. So it might be a model of Q at the end as well. For this, we have to be careful and choose properly the solution so that we don't add solutions to a fixed chosen instance of Q. And for this, we want to find the appropriate invariant. And a big part of the difficulty in a separation proof is to find the appropriate weakness invariance. So weakness property is just a collection of sets which is closed downward under the Turing reductions. So in particular, every Turing ideal is a weakness property, but there are much more. So being low is a weakness property because if x is low, so low means you have the same halting set as same degree of halting set as the standard halting set. So if x is low and x computes y, then y is low as well. But there are also other examples such that the collection of x which do not compute a fixed set A. So this is a weakness property. Or being hypermuon free, so which means being not so that every function that you compute is dominated by a computable function. So this is also a weakness property. There are many such examples, and there are and sometimes we have to cook very specific notions given a pair of problems. So given a weakness property, we say that a problem P, so in terms of instances and solutions, preserves the weakness property if for every weak set Z and every Z computable instance X of P, you can find a solution so that joined to Z, you are still weak. So you just have the proper weakness invariant. And it's easy to show, using the previous construction, that if P preserves the weakness property W, then for every weak set Z, you can create a Turing ideal which will satisfy P and contain Z. So you just start with the model of, you just relativize the previous construction starting with the initial model of the Z computable sets, and then you iterate, and you add more and more solutions to instances of P. And then, using this previous lemma, you can prove that if P preserves W but Q does not, then RC0 plus P does not prove Q, and this separation is witnessed by omega model. How do you prove that? You just take the set Z which witnesses the fact that Q does not preserve W, so which means you have a Z, and a Z computable instance of Q, so that for every solution to this instance, you will not be weak joined to Z. So now if you make a model of P which will contain this Z, this instance will not have any solution, this instance of Q will not have any solution in the model. It's easy combinatoric, easy to check. So we have a general framework, but now let's try to apply it to actual weakness properties and actual problems. And the first one, and the most known one is most well-known one, is cone avoidance. So cone avoidance is basically to separate problems from ACA0. So ACA0, that's Demir also already mentioned, means arithmetic comprehension axiom. So you just take RCA0 and you add the comprehension axiom for all arithmetic formulas. And so it's part of the big five, and it's equivalent to many natural statements, in particular, so Bolzano-Weierstrass, Koenig's lemma, when you work at arbitrary finitely branching trees, or Ramsey theorem when you start to look for triples, and so on. And in particular, the halting set, so for every set in the model, the halting set relative to x is sigma 01 definable. So by the comprehension axiom, the halting set will also belong to the model. So the models of AC naught are closed under the Turing jump. And actually, by post theorem, any arithmetic formula can be obtained by sufficient iterations, finitely many iterations of the jump. So actually, over RC naught, AC naught is equivalent to the statement for every x, the jump of x exists. So there exists a set y, so that y is equal to the jump of x. So this way, it's more formulated as a pi12 problem, just like that, with only one instance. So well, no, not only one instance, but so each instance has only one solution, which is the jump of it. So if a pi12 problem P preserves this weakness property, so the collection of Z which do not compute the halting set, then RC naught plus P does not prove AC naught, and this is weakness over omega models. Why? Because any model of AC naught contains the empty set, and because of this, then it contains also the halting set. So if you are able to show that you preserve this property, then you will be able to make a model of P which does not contain the halting set, and so which is not a model of AC naught. Actually, most of the time, what we exploit of the halting set is just the fact that it's not computable. So we prove actually a scheme of preservations. So in the sense that a problem admits cone avoidance if for every set Z and every cone, so every set C which is not Z computable, for every instance, every weak instance of your problem, you can find a solution so that your set C is still not computable with the appropriate relativization. So it seems to be a bit technical because of the relativization, but really it means that if a set is not computable, then for every computable instance, you have a solution which still does not compute your cone, and you close it so that you can iterate it. And it can be formulated in terms of our previous preservation framework, saying that you admit cone avoidance if and only if you preserve WC, so the set of Z which do not compute C for every set C. So of course, if C is computable, then this collection is empty, and this is vacuously true because it's a universal quantifier. So it's stupid. But the interesting cases are when C is not computable, then this class is non-empty. So let's make let's consider a few examples of problems, or especially about notion of forcing. So the strategy will be to look at simple examples, and then we'll see that all these proofs of cone avoidance have a similar pattern. So we try to extract this pattern, try to extract the core ID, and then we are going to apply it to make a non-trivial applications to the pigeonhole principle. For this, we need to talk a little bit about forcing in computability theory. So forcing is always a scary name for those who are not familiar with it, because it's always associated to set theory and to independence proofs. But actually, forcing itself is not a complicated framework. It's just that the idea is given a universe to try to extend this universe with another object while preserving initial properties of the universe. And because in set theory, the theory of set theory is complicated, it has many axioms, and so you have to check many things to make it work. And so forcing is complicated because it's applied to set theory, but it's not complicated when you apply it to computability theory. And especially because one of the nice features of computability theory is it's very incremental in the learning of forcing, in the sense that you first learn how to do the finite extension method. So you want to build an infinite object, and you make it by approximation by initial segments, and you have requirements, a countable collection of requirements. And the idea is, given an initial segment, you want to extend it so that whatever the remainder of the construction, your requirement will be satisfied. And you iterate it like that. And forcing is just a systematization of this approach. And so you just abstract it a little bit by saying, I want to build an infinite object. And so I approximate it by a partial order of finite or partial approximation of the object. And this order means that if P is smaller than Q, it means that P is more precise than Q. And so here in computability theory, for every approximation, I will associate a denotation, which will be a collection of sets, which will be the candidate objects that we're going to build. So contrary to set theory, where we had the full filter, here we are just going to interpret a filter into a set, and this is the set that we're going to build. So given an approximation, we have this denotation of saying, here are the possible objects that can be built from this approximation. And we want that if Q is smaller than P, then because we are more precise, it means that we have less candidates. So the denotation of Q is included in the denotation of P. Really think of P as an approximation. And so a filter, so it's a collection so here again, we work with filters, but you can really think of it as a decreasing sequence of conditions. So because every countable filter is in one-to-one correspondence with a decreasing sequence of conditions. So a filter is just a collection of approximations which are compatible in the sense that for every two approximations, you have a more precise approximation which is compatible with those two, and you are closed upward. But really think of it as a decreasing sequence of more and more precise approximation of the object you build. And at the end, the denotation of your filter will just be the intersection of the denotation of your approximations. And if it's well defined, so if for all the forcing notion that we are going to consider, for every maximal filter or sufficiently generic filter, this will be a singleton. There will be only one object in it. And this is the object which is associated to the filter. So a dense set of conditions is, technically it's just a set of conditions so that for every approximation you can find a refinement of this approximation which will belong to this dense set. But really think of it as a collection of approximations so that whatever your construction of an infinite decreasing sequence, it will never be too late to intersect this dense set. Which means that let's say you have a countable collection of dense sets. And you want to make a decreasing sequence which will intersect all these dense sets. So look at the first one. You know that there exists an extension which belongs to this dense set, so you take it. Then you could consider the next one. You know that there exists an extension, and you take it, and so on. And because you are dense, whatever the finite decreasing sequence you have done, considering the next one, you will always find an extension which will intersect this set. So it's never too late. And then there is one of the nicest features of forcing is the fact that the approximations are able to already decide very complex or very elaborate properties of the resulting objects already at this stage of the construction. And so this, and especially in computability theory, in simple cases, we even have an even stronger notion of forcing where actually you force a property if for every candidate object in your condition, the property already holds for this. It's not true in general. If you look at complicated formulas, this forcing relation will not hold anymore. So it's not general enough. It's a bit too strong. But for sigma 01, pi 01, even sigma 02 properties, actually this is sufficient. And so really think of it that way. It means whatever the remainder of the construction, the property already holds. You know that the property will hold because it holds for all the possible candidates. Okay. And so the simplest example of forcing notion is Cohen forcing, which is just the partial order of finitary strings and ordered by the extension. So here, just be a little bit careful because we take the extension, which means that you are a decreasing condition if you are an extension of your string, of your binary string. So a condition is just a string denoted by a Greek letter. So tau is an extension of sigma, meaning that sigma is a prefix of tau. And the denotation of sigma is just the collection of all possible x which have sigma as a prefix. So all the candidates are, well, just during the construction, you are going to extend sigma further and further. You are making larger and larger initial segments. And so all the possible candidates are all the set that you could obtain as having sigma as initial segments. And so we can prove a cone-avoidance theorem for, so it's not really cone-avoidance in the precise sense that we define, but we can show that if C is a non-computable set, then for every sufficiently Cohen-generic set G, C is not G computable. And for this, all we need to prove is the following technical lemma, saying that if you have a non-computable set C, and given a Turing functional phi E, the following set is dense, the set of sigma, so that sigma forces phi E of G to be different from C. If you force this, so if this set is dense, then if you are sufficiently generic, you are going to intersect all these dense sets. So there are countably many of these because there are countably many Turing functionals. And then it means that G cannot compute C, because if it computes C, there exists a Turing functional so that phi E of G is equal to C, and contradicting the fact that you intersect your dense sets. Okay? So let's just prove this technical lemma. So you have a condition, sigma, which is just a binary string, finite binary string. Consider the following CE set, or sigma-01 set, the set of all pairs, xv, such that you can find an extension of your initial segments, which makes you halt on the input x and output the value v. Okay? So actually, so x is an arbitrary integer. Let's say that v is a 0 or 1. Let's consider only 0, 1 valued functional. Then we have three possible cases. The first case is there exists an input and a wrong value which belongs to this set, which means that actually there exists an input so that we can find an extension which makes you halt and diagonalize against C. If so, if we are in case 1, then you just take the tau which witnesses the fact that you belong to W, and you have an extension which forces this inequality, forcing in the strong sense that I mentioned. So in particular, tau belongs to this dense set, to D. In the second case, there exists an input so that the good value does not belong, the good pair does not belong to a set W, which means that there exists an input so that whatever the extension, you will never be able to halt and output this value. Which means that from now on, so sigma already forces either a phi E of G to be partial on X, or to later halt on a wrong value, but in any case, it forces phi E of G to be different from C. Okay? So in this case, actually, we don't even need to take an extension. Sigma already forces the diagonalization. So sigma already belongs to the set D. And in the last case, if none of the two cases hold, then it means that W, this is just the sigma-01 graph of C. So it means that for every X, there exists, because case 1 does not hold, it means that when a pair belongs to it, this will be the good value. And because case 2 does not hold, it means that for every X, there will be a value which will belong to it. So which means that W gives a good description of C, but this is not possible because C is not computable. Okay? So really try to remember this structure and this trichotomy. Let's look at another example and work with trees. So weak Koenig's lemma is a restriction of Koenig's lemma to binary trees. So because we work in second-order arithmetic, we have to work with proper coding, but let's just assume we have fixed an appropriate coding of the binary strings and so on. So still, 2 to the less than omega is the set of finite binary string. We call a binary tree just a collection of binary strings, which is closed under prefix. Okay, so this induces a tree structure. And a path through T, so usually in graph theory, we consider that a graph is a set of nodes. Here, a path is just an infinite binary sequence, so that every initial segment belongs to the tree. So weak Koenig's lemma says that every infinite binary tree admits an infinite path. And so we are going to work with Jokersor forcing, where the partial order is the collection of all infinite computable binary trees. And so ordered by the inclusion, so you are more precise if you are a subtree of the other tree. And the denotation of the tree is the collection of all infinite paths through the tree. So the goal of the Jokersor forcing is to compute paths through trees. And we can prove what is called the cone-avoidance basis theorem, which says that if C is not computable, then for every computable infinite binary tree, you can find a path which still does not compute the set C. And for this, again, we want to show our diagonalization, so our density lemma, saying that the set of conditions which forces this inequality is dense, where the inequality just say that you do not compute C through the functional phi E. So first, you see that it has a similar structure. So given a condition, which is an infinite computable binary tree, define a sigma 01 set, but this sigma 01 set is defined a bit differently. It's a set of pairs so that there exists a level in the tree, so that for every node at this level in the tree, you halt and you halt on input x and equal v. Okay? And we have still three cases. So still, because this is a bounded quantification, this is still a sigma 01 set, so this is a CE set. So we have three cases. In the first case, again, you will be able to halt and to force to halt on the wrong value. So if x and the wrong value belongs to w, what does it mean? It means that there exists a level, so that for every node at this level, you will halt on the wrong value, which means that actually the tree T already forces the diagonalization. No need to take an extension. This is kind of a dual situation as for co-enforcing. In case 2, there exists, so a good pair does not belong to a set W. But what does it mean? It means that for this good value, for every length, you can find a node of this length so that you either diverge or you halt and are different from this value. But then look at the set of all such nodes. This is still an infinite binary subtree. And so you can take it as the extension, and this forces this diagonalization. Because whatever the path you are going to take, all its initial segments will be which will belong to this tree, and so you will never be able to halt and be equal to the good value. So,
what was the?
Sorry?
What were the conditions?
A condition is an infinite computable binary tree. So because the set of sigma 3, so that's so if you are very careful, maybe so it is the set of sigma so that what do you want? You want that for all so sigma so that so because this is a partial oracle, and by convention of partial oracle this is decidable. So I assume that if phi E of sigma on x halts, it is with less than length of sigma steps and all of this. So this predicate is decidable because sigma is a partial oracle, and so this is perfectly decidable.
Oh, so sorry, what is
this notation? So if you halt,
does it mean you only want number of sigma?
So because of the use property, if you halt with an oracle A, by the use property, there exists an initial segment of A for which you halt. There is some sigma. And so this notation means that you halt by iterating the oracle only on the values for which it's defined. But we can even strengthen the thing by saying, if you halt, then this will be in less than length of sigma steps, because by taking the use to be long enough. And so this is a decidable property. So in the second case, you can find, contrary to a co-enforcing for which the condition already forced the negation, here you can take an extension, so a subtree, infinitary computable subtree, which forces the inequality. And in the last case, it just comes from the structure of this. It's just that it's a sigma 01 set, and it's a graph for C, and you get a contradiction. So you start to see that there are some common structure in these proofs. And so a forcing question for a condition, so it's a relation between a condition and a formula. So not only sigma 01, it could be for arbitrary formulas, so that if it holds, then there exists an extension which forces the formula. And if it does not hold, then there exists an extension which forces an extension of the formula. There are many ways. Sorry. So a forcing question It's just like a variant of the forcing relation, so that if it holds, there exists an extension which forces the formula, and if it does not hold, there exists an extension which might be the same condition which forces the negation. Sorry?
Is the lemma?
It is a definition. It is some kind of specification.
So it shouldn't be called lemma.
No, yeah, actually, yes. It shouldn't be a lemma. It's a specification of a forcing equation. And it's not the forcing equation, it's a forcing equation. There are many ways to define forcing equation for a notion of forcing. And so actually, given a property, you can divide the set of conditions into three categories. The ones which already force the property, the sigma 1 property, the ones which force the negation of the properties, and there is in between conditions for which it's not decided yet. So there are some extensions which forces this property, and there are some extensions which forces the negation. And so a forcing question is just a dividing line which belongs to this blue side, and which decide between these two. And so in the so in the Cohen side, how did we define the forcing question? We were saying, is there an extension so that I can satisfy my sigma 1 property? So in some sense, he was saying, is there any way to satisfy my sigma 1 property? And it was answering no if there is no way to force it. So it's the dividing line is here. So in saying that if the answer is no, it means that you already were forcing the pi 1 property because there was no way to find an extension forcing it. But if there is any way, let's put it on this side. And for the Jokic-Shor forcing question, it was the opposite situation. So we're saying, do we already force the sigma 1 property? So is there a level in the tree so that everybody everybody satisfies my sigma 1 property? So then there is nothing to do. But if not, then we are going to restrict your tree and force the pi 1 property. So it's on the extreme opposite. So fix the notion of forcing. We say that a forcing question is gamma preserving for a family of formulas gamma. If for every condition and every gamma formula, so think of gamma as sigma 1, for example, the relation forcing question, so P forcing question phi of gx is sigma, so let's take gamma sigma 1. Then this is sigma 1 uniformly in the parameter x. It does not need to be uniform in the approximation, but it has to be uniform in the parameters of the formula. We can show that if you have a notion of forcing which admits a sigma 1 preserving forcing question, then you are able to prove this density lemma, which is necessary to prove conavoidance. So for every non-computable set C and every Turing functional, the following set is dense, very abstractly. So here is still the same proof structure. Given a condition, consider the following sigma 1 set, and it's sigma 1 because you are sigma 1 preserving. The set of pairs xv, so that you answer yes to can I find an extension which will input x hat and output v. So if x and a wrong value belongs to w, by specification of the forcing question, it means that there exists an extension which will force you to halt on input v and output a wrong value. And if we are in case 2, it means that there exists an extension which will force you not to halt and be equal to c of x, so which means either for you to diverge or to halt on the wrong value. And in the last case, because this is sigma 1 preserving, you have a sigma 1 graph of C, which is not possible. So you have density. And this is abstractly from having a sigma 1 preserving forcing question. Okay, so in all two cases, we have extremal forcing questions. But let's try to apply it to a non-trivial example. And by non-trivial example, I mean the pigeonhole principle. So the pigeonhole principle says that if you make a partition of the integers into finitely many parts, you have an infinite subset of one of the parts. And there is this beautiful theorem from Demir and Karl, who says that if a set is not computable, then whatever the instance of the pigeonhole principle, so no effectiveness, no computability restriction of it, you can always find aside an infinite set which is in one of the parts, so that this set does not compute C. And it relativizes well. So in this problem, in this theorem, an input is just a set which is not computable, and an instance of your problem, so a two partition of the integers. And what you want to build is an infinite subset of one of the two sides. But of course, since you don't know yet what sides we are going to choose, we are going to build the two sides simultaneously. So the notion of forcing is a variant of what is called Mathias forcing. So we are going to build, so you are going to consider conditions so that you build two objects simultaneously. So F0 will be an initial segment of a homogeneous set for color blue. F1 will be an initial segment of a homogeneous set for color red. And X is an infinite set of integers, so that from now on, the elements that you are going to add to F0 or to F1 have to come from X. So originally, X is just a set of integers, and these two are the empty sets. So structurally, what we ensure is that the Fi are finite, X is infinite. You also want that the maximum element if Fi is smaller than the minimum element of X, just for continuity purpose, because you want that once you have fixed F0, F0 not only has fixed the elements which are in it, but also the elements which are not in it up to a certain point. And you want structurally that Fi has the appropriate color, so F0 is color blue, F1 is color red. And there is this weakness property that will be justified later. And depending on the situation, we are going to use a different weakness property. So we want the set to be weak. An extension is just, so you are an extension if you increase E, so Fi becomes EI, so you add new elements to it, and the new elements you added to it come from the reservoir, so this is X, and you restrict the reservoir further. Not necessarily properly, but so it's a kind of weird notion of forcing because you build two objects, so a set G0 and set G1. So the denotation will be a pairs of sets, so that the initial segment of G0, so F0 will be an initial segment of G0, F1 will be an initial segment of G1, and what remains from G0 comes from the reservoir, and what remains from G1 comes from the reservoir as well. Okay? And you can check that you have still this inequality. So if you are decreasing sequence, it means that you are more precise. So here now the forcing relation is again something for two. You have two sets, two formal sets. You force a relation if your formula holds for every pair of sets. Okay. So still, we want to prove. So we are going to prove the following. We want to ensure the following requirements, which will be disjunctive requirements. We want that for every pair of Turing functionals, phi E0 and phi E1, we want either on the blue side, phi E0 fitted with J0 not to be equal to C, or phi E1 on the red side with G1 not to be equal to C. And if you are able to satisfy all these pairs of requirements, then actually either the blue side or the red side will not compute C. Why? Because if both sides computed C, then there would be witnessed by two functionals, and this appropriate requirement would fail. So what we want to show is that the set of conditions which force this disjunctive requirement is dense. So it's a slightly different situation. So, and here again, it does not fit perfectly in the framework in the sense that this is a disjunctive forcing. So we are going to design a disjunctive forcing question. So a disjunctive forcing question is of the form phi 0 or so phi 0 of G0 or phi 1 of G1. And here is the specification. If it holds, then there exists an extension which forces one of the two sides. Or actually can force. If you force the disjunction, then it means that actually there will be an extension which will force one of the two sides, so it's equivalent. And if it does not hold, then be careful. It doesn't mean that there exists an extension which forces the conjunction of the two. It means that there exists an extension which forces the negation of one of the two sides. So be a little bit careful and not be fooled by this disjunction. How to design such a disjunctive forcing question? So, yeah, let's just suppose we have such a thing before, and we have designed a sigma 1 preserving a forcing question, a disjunctive forcing question. Then we are going to be able to prove this following density lemma. So, yeah, I mean, the proof is exactly the same. You just consider this disjunction and you have this 3-case analysis, so there is no need to go too much into details. Let's just focus on how do you define this disjunctive forcing question. And the issue is that naturally, the way we would like to design it is to say, is there some side, and is there some extension, so finite extension of your initial segments on this side, so that your formula holds. But the problem is that here you want your extension to be on the appropriate color. So if it's side blue, then you want to take only elements on the blue side. But A has absolutely no computative restriction. It can be very complex. It can compute the set C in particular. So you are not allowed to make the formula depend on the set AI, on the instance. So you have to be a bit more careful in the definition. And the idea is to make an over-approximation. The over-approximation is saying, okay, let's try for every possible instance, instead of asking for this instance. Let's say, for every 2 partition, can I find a side, and can I find some extension with respect to these 2 partitions so that it holds? And at first sight, it's even worse. I mean, this formula is starting with a universal quantifier, second-order quantifier, so it's very complex. But actually, this formula is just sigma 01 with relative to the reservoir. Why? Why? Because simply by compactness, actually, this formula is equivalent to saying, is there a level so that for every finite 2 partition of this level, you can find an extension for which it holds. So you can translate it, thanks to compactness, into a sigma 01 formula. I'm sorry, I'm going a bit too fast for this translation, so let's just write it properly. This formula is equivalent to say, is there some L, so that for every B0 union B1 equal to, let's say, 0 to L, and then you have just the remaining formula. So there exists some side, there exists some EI including to X intersection to BI, so that phi R, whatever you want, holds. So you have an existential quantifier, then you have a bounded quantifier, bounded quantifier, bounded quantifier. And so this is sigma 01 with parameter still this set X. So why is it equivalent? First of all, if this holds, it should be clear that this holds as well. So the less trivial part is, if it does not hold, if it does not hold, why does this not hold? Suppose this does not hold, then it means that for every length, you can find a 2 partition of this length so that you have the negation of this. But then you can build a tree of 2 partitions so that at the level L, you have the 2 partitions of 0 to the L, and witnessing the negation. And so this forms a tree of 2 partitions for which you cannot find some EI on any side for which it holds. And so actually by Koenig's lemma, you can find an infinite 2 partition witnessing this failure. So it's really compactness. Okay. So now we can make let's make the case analysis. So in first case, if it holds, then because we made an over approximation, it's simple. You just take the 2 partition to be the actual 2 partition, and we design it so that to say, is there an extension which satisfies what we want? So it works. Okay. So the case 1 is the simple case, but the case 2 is the more tricky case. It's more tricky because it may fail. Because it's an over approximation, it may fail because of a 2 partition which has absolutely nothing to do with the original 2 partition. It may be because of some 2 partition B0, B1, which is absolutely not related to A0, A1. So, but what we can do is actually the collection of all the witnesses of failures, so of all those 2 partitions, has a nice description. It's a pi01 class. And thanks to our Joker-Sensor theorem, actually we can find a witnessing two partition which still does not compute your set C. And what does this two partition tell you? This two partition tells you that if from now on if E1 if E0 is compatible with B0, then the property phi0 will not hold, and same for phi1. So saying if you are compatible with my two partition, these two partitions which have nothing to do with A0, A1, then you will have the negation of the formula. So the idea is to say, let's try to be compatible with both instances simultaneously. So we continue to be homogeneous for A0 or A1, and we restrict the reservoir X to either B0 or B1, depending on which one is infinite. So if we take this, let's say that BI, X intersection to BI is infinite, then it means that from now on, every set that you are going to add, so let's say BI is B0, every set that you are going to add to F0, it will be something which is included in X intersection to B0, and so the negation of phi0 will still hold. So it's the beauty of the argument of saying, we make another approximation to simplify the forcing question. So if it holds, it's super. By design, we can find an extension for which it holds. And if it does not hold, then we can find a witness of failure, and we try to satisfy this witness of failure at the same time as we satisfy our original instance. And because we satisfy the witness of failure, then the negation of the formula will be forced. So let's just summarize what we know so far. We have this definition of forcing question and notion of forcing, and we have this correspondence of saying, if you are sigma 0 1 preserving, then you admit conavoidance. Conavoidance is the sense that you can prove that if you are sufficiently generic, then you are not going to compute any fixed non-computable set. And I think that it's just time. So let's just stop now.